a function phi from one ring to another ring is called a ring homomorphism if it's operation preserving. Just like with groups, nothing about being one-to-one and or onto. Though if we did assume that it was one-to-one and onto, then we'd call it a ring isomorphism. But homomorphism just means operation preserving. But remember, with rings, there's two operations. There's two operations to preserve. Yes, you would want them both preserved. So there's two equations to write down. One with respect to addition. Phi of R1 plus R2 is phi of R1 plus phi of R2. And one with respect to multiplication. This needs to be true for all R1, R2 in the ring, capital R. So it's doubly operation preserved. Preserves both addition and multiplication. And as an example of something you should be able to prove, a theorem you might say from this, I'll label it as a theorem. It's really just one part of a bigger theorem in the book. Suppose, let's go ahead and call it K, kind of like we did with group theory, is an ideal of S, then the preimage of K is an ideal of R. How could you prove this? You could use the ideal test, though if you're going to do it really from scratch, you'd also want to use the subring test first, because the ideal test assumes that it's a subring. Actually, it's good enough even to use the definition of an ideal, which involves two things: show it's closed under subtraction and show it's superclosed under multiplication. This will be the idea of the proof. First, let A and B be in the preimage. To show it's closed under subtraction, I need to show A minus B is in the preimage. What does that mean? First of all, this means phi of A and phi of B are in K. Right, draw a picture if you're feeling confused. Here's R, here's S. K is over here. It's an ideal in S. The preimage is over here. You're trying to show that's an ideal in R. You're assuming K is an ideal. That means it's a subring as well. That means it's closed under subtraction. You can say phi of A minus phi of B is in K. But because phi is operation preserving with respect to addition, which, remember, subtraction is the same as addition, it's just adding additive inverses. That means phi of A minus phi of B equals phi of A minus B. And this implies that A minus B is in the preimage, because it's, when you plug it into phi, you get an element of K. That's enough to say that this implies this, therefore the preimage is closed under subtraction. Is it superclosed under multiplication? Let A be an element of the preimage, and let R be an arbitrary ring element in R, not necessarily in the preimage. Is the product R times A and also the product A times R in the preimage? That's what you want to show. This implies phi of A is in K. Once again, just like we used in the first part, we've got to use the fact that K is an ideal somehow. You got to use that assumption. How do we use it up here? Since we knew phi of A and phi of B were in K, that meant their difference was in K. K was closed under subtraction. We're trying to show the preimage is superclosed under multiplication. Probably we need to use the fact that K is superclosed. R is in R, it's not in the preimage, but it's still an element of R. I can still plug it into phi. Phi of R is an element of S. Since K is an ideal, oh, this means it's superclosed. If I multiply these two things, they're both in K. So the product is in K, and I can do it in either order. I'm not necessarily assuming either R or S is commutative. So I do need to write both of these things. They're not the same thing. Because I'm not assuming R or S are commutative rings. Write both of them, use an and. What else do you always have to do in these proofs? You always have to use operation preserving. We did that up here. We can do it down here with multiplication. Phi of AR is in K, and phi of RA is in K. And that does it. That means AR and RA are in the preimage. Of K under phi. That proves that preimage is superclosed. To use the ideal test, technically you want to show it's a subring first. Show it's closed under subtraction. Show it's closed under multiplication. Actually, in doing these two steps, I kind of combined the subring test and the ideal test into one. I don't have to show the preimages just closed under multiplication. I can show it superclosed. So I can show both it being a subring and an ideal at once by doing these two steps.